Miguel, do you have any favorites or anything that you've come across, tried? May have. Oh, okay.
Yeah, I'm here. I don't. Usually I don't. Have been a while since I just take things from internet. So I usually try to just ask my coworkers, the real life problems with the tech that I'm asking about. So I'd rather be I'm in a bunch of communities. So if I can ask a question to somebody that can actually talk to me rather than random internet, because usually what is the internet is the most basic stuff, right? The most things that everybody finds. That's why you find it in Google, because everybody has that one issue. So at some point you stop having that one issue, those kind of issues, and usually the answer becomes more nuanced, and it's better if people can Google a little bit back and forth.
Yeah, I think that's a great point. But I was just wondering in general, like if you were interested in problems in general, not specific issues that you're either facing because of work or some other, school assignment or things like that, but websites that you may have come across. And these could be even like brain teasers or puzzles or, as I said before, mathematical problems, scientific problems. I have tried a couple of programming oriented websites, but I'm not as familiar with.
No, I see what you mean. No,
Yeah.
I actually found this one that they tried. I think it's called Egg something. I don't know, just something. I don't remember.
Yeah, look it up.
I tried to find it. They have like a bunch of answers to exercises of math books. That's one of the many math books don't have answers anywhere. So they try to make you pay to make it easier.
Okay.
And let me see if I can find it. It's very good. It's
Okay.
obviously
Yeah,
complete because it depends on the edition many times. So you go to Amazon, buy the latest edition of the math book,
right.
and it turns out that's the one edition that nobody has the answers for.
And usually textbooks, they don't make the answers available publicly, right? They're only available for teachers, like authorized people. Alan, we were just discussing responses to this question. So if you have any websites that you would recommend for either working on problems or helping with problem solving. So Miguel found the website he was thinking about, check.com.
So that website, the front page sounds like something for high school, but they do have things like linear algebra done right. Like this is a very abstract math book. So they have like almost anything, and they do ask you to pay for certain. I don't remember what. I had to pay when I was going through the linear algebra done right. I did pay because it made it easier for a month at least.
Okay.
So
Arthur has mentioned Google's yearly Advent of Code and Stack Exchange, puzzling Stack Exchange plus regular Stack Overflow. So does Stack Exchange have like a special section or area for problems?
So it has at least two that are relevant to your interests, I think. I enjoy browsing the puzzles Stack Exchange, puzzling the Stack Exchange.
Oh, I see what you're saying, right.
Which is not programming, but just general stuff. But some of the problems end up being numeric things that are amenable to, like, well, I have no idea how to do this, but I can write a program to do it. Which is generally not in the spirit of, like, they even have a no computers tag that you can put on a question to say, I know this is easy, it's find the anagram of whatever, but, no computers for this one, which are the most fun to write a little Python program for or whatever. And then they do also have programming puzzles and code golf, which I think is codegolf.stackexchange.com. I'm not sure what the URL is. But that's like write the smallest program to compute X, where they typically will post problems that are not exactly algorithmic problems usually. They're usually something really simple, like, display this text, but do it in the smallest way possible. Or, tell whether a number is even using the smallest number of instructions, that kind of thing.
Okay. And what about Google's advent of code? What is that?
That's a more like what we're talking about, programming competition, or, yeah, I mean, it's a competition in the sense that it has a leaderboard, I think. But it's basically every day they post 1 2-part puzzle during Advent, so it's an Advent calendar. And so every day through the month of December, leading up to Christmas, they post 2 problems a day, or 1 2-part problem a day. And they are algorithmic problems where they'll describe the algorithm you're supposed to implement and give you 1 large sample input that you can cut and paste into whatever program you write. And then you just cut and paste back the answer and it says, yes, that's right. Or
Okay. Yeah, that sounds really great. What about Alan? Do you have any recommendations or sites that you've come across that you've kind of enjoyed or like for either coding problems or puzzles or anything like that? Alan may have stepped away. Okay, so yeah, so let's get going. So today we are going to focus on the exercises. And here's the agenda. Pretty much these are the sections that we've covered so far, and we were really, just spend a lot of time on the reading and the discussion and then the examples in the visual debugger. So we haven't had a chance to look at the exercises so far, and that's what we're going to do. So these are the topics that we have covered, and the exercises are pages 24 through 28 of Fascicle 1. Hi, Deepa. We were just going over the agenda for today, but I did ask a question earlier, so let me go back to that slide so you can also look at it. I did paste the question at the top of the chat as well. I don't know if that's actually visible for people who join in late. Probably not. In any case, this is the question.
Yeah,
so I'm sorry?
the question is not.
So this is the question. So any website, no, the slide, is the slide visible?
the slide is the chat is sent. If you come in late, the chat starts wherever it starts.
Yeah, I guess the chat is truncated. So, but it's the same thing, right? What you see on the slide. So if you have any site or sites that you like for solving problems, and these could be puzzles, brain teasers, these could be coding problems, these could be problems in other areas of science or math or pretty much anything, or even sites that help you with solving problems, guides or tips and techniques, things like that. So yeah, anything, and feel free to add more responses if you can think of any more. Doesn't have to be just one. So right, so the focus today is hopefully we can solve some of these problems for the topics that we've covered, which is essentially MMIX instructions so far. And we've seen a bit of programming, but I don't think we'll see any problems that require to write like programs. It's really at the instruction level, like what can you do with these instructions, or like what do these instructions really mean, or covering corner cases. And so here's our usual procedure, and we won't really be following it today because we're not really doing any reading, at least together. We may need to go back into the text. We'll probably need to go back into the text and look at what these things were. But we'll do that in the context of solving a problem. So what I plan to do today, so I'm not sure how we'll, structure this in the future if we ever need to do this again, like just focus on problems. We may probably. And so what I was thinking was, so the first thing I did was I did write up a bunch of problems from the exercises section that I felt covered the material that we have discussed so far. And those were available to everyone in a shared Google Doc. That link is on the Meetup page, so you can click on that, you'll see the Google Doc. And then I also transferred it to the GitHub repo, and that link is also posted in a comment on the Meetup page. So I am going to share that GitHub document, which is in Markdown, but it looks pretty good. So I was pretty happy with that. And we'll just sort of go through those. I'm thinking since there's not a lot of people, we can just sort of do this together, go through problems, decide which ones we want to attempt, and maybe discuss them, work on them for a bit. If we get a solution, that's great. And we can decide amongst ourselves what a solution is, or if it's, a good solution. If we don't, then after some reasonable amount of time, we can decide whether we want to look at the answer and try to figure that out and maybe understand it and have somebody explain it. So that's sort of the gist of our structure today. So here's what Knuth says about his exercises. This is stuff that we had read before in one of our introductory meetups when we went over the preface and the notes on the exercises, but just wanted to, again, give his point of view. And from what we've read so far and seen of TAOCP so far, the exercises are really essential to getting the most out of the text because, as he says, it's a major part of the work. So what that implies is that a lot of the content is not just in the, in the sections and the chapters, but they're embedded in the exercises. So, and since the exercises are things that you have to work on, it's not apparent what that content is until you actually try them and, then maybe get some insight or then finally look at the answers. And so this is I think I may have mentioned, like, in the first session, one of the main reasons why I decided to spend a lot more time and focus on TAOCP was when I came across a reference to an exercise in volume 3 in and I don't think I mentioned the specific reference, but it was in the GNU sort program. So GNU sort, if you haven't used it, is probably the most commonly used sorting program in the world. And, it's so ubiquitous that people don't even realize what they're using. I think, it's at that level. It's like grep and sort and, a couple of other commands. It's right up there. And in the GNU sort program, its algorithm is based on a merge sort. And we'll go over merge sort if you haven't seen it before. But merge sort, the way they've implemented merge sort in GNU sort uses a technique that is an exercise in one of Knuth's sorting sections. I think the section on merge sort. And it's, it's this little, like, 3 or 4 lines of the exercise, but the solution to that has had so huge an impact in terms of its usage, right? So I was really impressed by that. Like, there's this little exercise, but it GNU sort's efficiency and performance sort of turns on the solution for that exercise. And we'll look at that hopefully when we get to sorting. We are in Fascicle 1 MMIX, which is the booklet, the standalone booklet that accompanies TAOCP. And we are going to look at the exercises on pages 24 through 28. And now I will share the document that is in the GitHub repo. How is that font size? Too big, too small, just right? Just right. Okay, cool. So yeah, so let's just go down the list. I think we'll try to avoid anything that is marked 30 or higher, maybe even like 25 or higher in terms of the effort or difficulty estimate that Knuth provides. So maybe like 00 through low 20s at the most. And you'll see some arrowheads that show up as this blue icon before a question. So question number 6 does have that. And these are taken directly from Knuth's text, and these are supposed to be somewhat more significant in terms of furthering your understanding of the material. So Knuth says, these are like strongly recommended exercises, and you should try them. So we will, try to attempt those as much as possible. But other than that, again, we don't want to spend too much time trying to work on a problem. If we don't get it within a few minutes, let's decide to either move on or look at the answer and then try to understand that. So let's just start with the first one. The binary form of 2009 is the sequence of bits. That's in base 2, obviously. So what is it in hex? So if somebody could just either paste the answer, type the answer in chat, or explain it verbally. Either way is fine.
By the way, I think this is a valuable question for some of the people in this. I'm assuming that some people are like, yes, I should know this.
I would say every question is valuable. If we go through it faster, that's
I question
fine.
number 3, but numbers 1 and 2, I think, are things that people who are taking this to be like, well, I don't know what bitwise operations are, but I want to learn. These are excellent questions.
Yeah, and Deepa has a great suggestion in the chat. So take them like 4 bits at a time and convert. Why would you use 4, by the way? Feel free to speak. Like, there's no reason why I mean, there's very few of us right now, so we should be able to sort of figure out who's speaking. So I'll just go ahead and add some annotation to that. So I assume 4 because, sets of 4 because you need 4 bits to represent 16 values, and so if we're asked for hex, those go up from 0 through 15 as digits, so that's 16 values, sets of 4, and what is the final answer?
F. The other one is D. And other ones. So while people find the answer, somebody knows if this convention of taking each 4 bits to be an hexadecimal is like a global convention. Is that how we all do it every time we see an hexadecimal somewhere in a computer? Is that what it's supposed to mean?
Yes, I mean the 0x whatever, pretty much these days universally right? I mean, there was a period in time, right, in the 1950s where this was not the convention. But these days, yeah, I mean, if someone says 0x ABC, they're talking about hexadecimal, and A always means 10 and B always means 11. Yeah, that's very standard.
Got it. Got it.
Yeah, what was the older convention, Arthur?
I don't know of any specific older convention. I mean, if you were doing like regular mathematics, you could use a little 16 subscript, right? Everyone's saying F. Did I miscount the number of ones here?
I think you missed 1 in the first. Oh,
No, I don't think I did.
okay. So maybe
This is almost 2 to the 11th. And so, yeah.
Let's see
1,
what we
0, 0,
have.
0.
So there's four ones in the first chunk from the left.
That's F.
Are you seeing something else in your? I mean, what are you looking at? Are you looking at some other
I'm
document?
looking at your screen. I
Okay.
see 1, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1. And so if you
So
take that,
1001 from the right, that's 4, and then 1. Oh yeah, you're right. You're right. So it's not F.
right, three ones in a row is 7.
So that's 7. So it's 7 D9. Wow. Yeah. I think let's fix that.
Yep.
Okay. Oh, that's why you had the 0 in the parentheses. I think that's what at least confused me. I thought that maybe you were using some kind of notation to mean that this is like 0x or something like that. But yeah, you're just filling in that slot.
Yep.
Oh,
Okay.
wait, so you start from the right. Is that what happened?
Correct.
I was doing it the other way around. I was doing it from the left.
But then when you get to
Left,
the right,
right.
then you've run out of digits. What do you do at that
Yeah.
point, right?
I see. I see. No, you know what? I didn't count the last one. Probably there are 4, and I forgot about it. So it's the other way around. I see. Good
Yeah.
point.
Yeah. Yeah. You have to start chunking from the right to
From the right.
ensure that you have full chunks of 4 bits.
So this 0 exercises might be a little dangerous because I just said, yeah, I know what this means, and I stopped thinking about it.
Yeah. Yeah.
And it turns out that I was missing something important.
There you go. Speaking of older conventions, I do notice like in older either text or source code, octal seemed to be much more popular than hex, and I'm not sure when that shift sort of happened. Like now, people tend to work more with hex rather than base 8 when they want to sort of figure out the binary thing.
That actually reminds me that I do know one alternative convention for hexadecimal from the 1950s, 60s would be an overbar. So it would go 0 through 9, and then they would just start over at 0 bar, 1 bar, up to 5 bar. And that would just be the way you write 10, 11, 12, 15. Right?
Yeah, I'm pretty sure that there were also probably a lot of mathematical conventions that people were following, like different sort of mathematical syntaxes and notations. But then, as computer science and sort of programming took over the world of binary manipulation, then it's whatever programmers do that becomes a standard. Deepa asks hex because it is 8-bit is 1 byte. So actually, 8 bits is 1 byte, but I think it's hex because I guess it's related to that. You can easily divide 8 bits or 1 byte into 2 4-bit pieces, and so it's nice to have that sort of boundary, even boundary for bytes. So I think you're right. Like that's why hex did become popular, and it could be because the definition of byte wasn't that universal. Maybe in the 50s, like there were some alternative definitions of bytes, I think, floating around, and that may have gone along with that.
and not even bytes, but just words of memory in general. The whole idea of just having this little tiny byte was a relatively new innovation. Originally, you would use as many bits as you needed to do math, and you would write a whole word to memory at a time. The idea of chunking it up into like, oh, up to 255, what can I even do with that?
Yeah. All right, let's go on to number 2. So this is something that we had mentioned in passing when we talked about the Unicode snippet early on, but which of these letters, uppercase A through F and lowercase a through F, are odd when considered as hex digits, and then secondly as ASCII characters. So as hex digits, what would be the answer? A is 10, so that's even. So B is 11, so that's odd. So it'll be B, D, and F uppercase. Same thing for lowercase letters, right? Okay.
And I should point out that as far as hexadecimal is concerned, since we're asking about the traditional representation, there is no difference in traditional representation. Uppercase A, lowercase a, they're both A as far as we are concerned when we're talking about hexadecimal.
Okay, so now it gets a little tricky. As ASCII characters. So first of all, how do we know what the value of these letters is as ASCII characters? What would we do?
We ask Google.
We ask Google, exactly. So yeah, let's try that. What is A in ASCII? Does Google have a straight answer to that? Like first hit?
It's pretty.
Of course, by Google we mean Wikipedia.
Or yeah, I would. What I would
But
actually.
does it give you the number like in your face?
Not exactly in your face, but pretty darn close.
Okay.
It gives you a quote from the asciicode.com.ar.
Okay.
Which tells you that it's number 65.
Number 65 for uppercase A. So
That's
uppercase A then is odd as ASCII. What about uppercase B?
Is the next one, right? So
it is the next one. Okay, so that helps us a lot. So if they're in sequence, then if A is odd, then C is odd, and E is odd, uppercase at least. What about the lowercase a? What is that?
Well, I'm assuming that there has to be an offset, and that's pretty much plus or minus. I probably it's minus whatever, right? 65 minus whatever plus 1 plus 1 plus 1 plus 1.
Okay, what does Dr. Google say?
Deepa's already got it.
Deepa's got it. Oh, okay. They are consecutive from 65 onwards, and 97 is lowercase a. So 90. Okay, so A is. Does that add up? Like if you add 26 to 65?
Because why would you add 26? Right? 26 is not a special number to the computer. What is a special?
I'm saying that if they were consecutive, like you have the uppercase letters A through uppercase Z, and then you had lowercase a, and
then if you immediately started the lowercase letters right after uppercase Z, then in order to convert from upper to lower and back, you would have to add and subtract 26, and that's a very weird number as far as the computer is concerned. It wants to add or subtract a power of 2, right? Because you can do that by flipping a single bit.
Okay.
So you've got just like numbers have a sign bit, you've got a case bit.
Okay. Okay, so that sounds good, but what that implies is that they're not together, right? All the letters are not together.
Well, all the uppercase letters are together, and all the
all the uppercase are together, but then the lowercase are not immediately following the uppercase.
Right. You have a gap of what would it be? Six blank spots you have to fill in with punctuation.
Oh yeah. So then it's not as simple as just adding 26 to 65 and then saying, oh, that's going to be, because it's an even number that you're adding to an odd number, so then it has to be odd too. That logic doesn't work. So there's some other thing at play. Lowercase a is 97, so it is still odd, and we do get lowercase a, c, and e as odd. Okay, great. Number 3 is a fun one. 4-bit quantities, half bytes or hex digits are often called nibbles. Suggest a good name for 2-bit quantities so that we have a complete binary nomenclature ranging from bits to octobytes.
So what is a nibble other than this? So why is that word relevant? First time in my life that I have heard nibble. Nibble.
I think it's just a fun problem.
Like
He's just asking for you to come up with names, and he's thrown out some suggestion, like people have called 4-bit quantities nibbles. I guess following from bytes, right? So 8 bits are bytes, and a nibble is, well, if you spell it with an I, it's like a small byte. And so you turn the I to a Y, make it more, like programmer oriented or code oriented, computer oriented. And so, yeah, so what are your suggestions for 2-bit quantities? So Arthur's given some bit hacks for case changing.
Number 3 is one of the questions I would have skipped. It's obviously the right answer. I will suggest tidbit.
Tidbit,
So,
okay.
Of course, because this is Knuth.
Okay.
See what they.
Any other quick suggestions? Just throw anything out there.
The official answer suggests nip.
Oh, really? Okay. I think I did add my answers, a couple of these to the shared doc, and I think I said dibs. So yeah, that was mine. All right. As another nomenclature, this is more like Googling stuff, but yeah, it's good to know. I think if somebody wants to Google these, what are the official names for these larger 1,000 times of these units, bigger than a kilobyte and a megabyte? So obviously, gigabytes are pretty common now. So after gigabytes, bigger than gigabytes, what's next? You can just type that in.
Although this is another one that is good for people who are coming here to say, I need to know the stuff for the interview or whatever. This is a real one, right? Kilobyte, megabyte, gigabyte, per billions. And then when we get to trillions, we have terabyte.
Yeah, terabytes are pretty common now too, with hard disks being, pretty much terabytes. Okay, after terabyte, bigger than terabyte.
Petabyte.
Petabyte. Okay. So
petabyte.
Right. So petabytes. Not sure if you can buy a petabyte disk right now, like for personal use. But certainly, I think like commercial disk storage systems, I think, do come in petabytes right now. And then what is bigger than a petabyte?
Be an exabyte.
Exabyte, yeah, that's right. And exabyte, I think, is a company also, like a storage company. But yeah, I think you can get like, and you hear of these exabyte scale problems. I guess it means like really big data, big data problems. So exabyte scale. That, I think that's sort of the limit right now where we are at in terms of the boundaries.
But not the limit for words. Then after exabyte is the zettabyte, and then the yottabyte.
Okay, so zettabyte and then yottabyte. Okay, so
yeah.
I have not heard those in.
I found them in the Wikipedia.
Yeah, I'm not sure like what scale that would be or when we would reach
it. It's to this, yeah, it's like the same scale, right? Like 1,000 exabytes, 1,000.
Yeah.
More or more.
Yeah, I'm sure before long, you know, we'll be talking about them. All right, so number 5. Have a look at it. I can read it if alpha is any string of zeros and ones. So we've got, you know, some bit representation. And then let S of alpha and U of alpha be the numbers or the integers that it represents when regarded as a signed or unsigned binary number. So S of alpha is whatever that signed value is. U of alpha is whatever that unsigned value is. And then if X is any integer, we have this statement. If and only if means we have to show both directions. So assuming the equality on the left, which is that we're looking at the signed value and calling it X, then show that X is, and those, that triple equal or the triple dash sign is called congruent or congruency, or so you would read it as X is congruent to, and then you would say the right hand side, which would be U of alpha modulo 2 to the n, and X is between these two numbers, where n is the length of alpha. So there's a lot to process in just the statement. Does somebody want to summarize what the problem is? Whatever you've understood so far, you don't have to, you know, explain the whole thing.
So,
yeah.
No, I definitely cannot explain the whole thing.
Yeah.
So from what I remember from what I'm seeing also in the book that is open in front of me. So that statement, X is congruent with unsigned alpha plus module 2n. So so that means that is that X. I had it. I lost it. So
no worries. I think that's a great idea. Let's take like maybe pieces of this thing and understand as much as we can about those pieces. So let's.
So what I got.
Yeah. Go ahead.
Hold on. So sorry. So what I get is that that's equivalent to say that X minus 2 to the n multiplied by X, the ceiling, not the ceiling, the floor of X divided by 2 to the n is equals to unsigned of alpha minus the unsigned of alpha, you know, the same thing but with unsigned of alpha, the floor of unsigned of alpha divided by 2 to the n, and from there I will go somewhere.
Are you trying to explain the whole that?
I'm trying to decompose the thing, right? Like.
Okay, so let's look at just that congruency. Where it says X is congruent to U of alpha modulo 2 to the n. Could somebody type into the chat what that means?
I'll point out here that I don't think this exercise is really that fair, because it is asking you to prove something about these S and U notations, which I went back and said, okay, well, if we're going to prove something formally, let's see how he formally defined S and U. And it turns out he didn't really. He just says S denotes the signed integer corresponding to the bit pattern X according to the conventions of 2's complement notation, which he never defined, as far as I know.
No, he does. He defines 2's complement as the
I mean, we know what it
as the
means.
value
We
minus
but
2 to the n. So that is in the text. He does define it.
oh, okay. Maybe it's
So,
just not
so,
in
the,
this fascicle.
so does that mean that unsigned of alpha is equivalent to the sign of alpha minus 2 to the end?
Could somebody find that definition? I'm going to look for it too. I think it's in it is wherever he introduces the term 2's complement. So that would be very early on
Could
in
we,
section. Um,
Because that is how you're going to have to eventually do it if you want to actually prove this, is you have
Yeah.
to start with the definition, which is going to be something in terms of summing up some powers of 2.
Yeah, so I see it on page 4 of the fascicle, and that's where he defines 2's complement notation.
I see some examples.
Do you see where in italics?
Yeah, 2's complement notation
2's
in which the leftmost bit indicates the sign. If the leading bit is 1, we subtract 2 to the end to get the integer corresponding to an n-bit number in this notation.
Yeah, so that's the definition. So
Well,
if
find
the
something
leading
that
bit is not 1, meaning it's 0, then it's whatever that number is. But
which
whatever.
he hasn't defined.
Hmm?
Again, I know what, but as far as
You're not happy with that
we're going to end up
definition?
making up our own mathematical definition for it here.
Okay, so that's
so that we can prove
so
it.
yeah, so I guess you're right. Like there are two parts to this. One is 2's complement, but note over here, actually, he doesn't talk about 2's complement in problem 5 at least. It's mentioned in problem 6. But in problem 5, he's talking about signed and unsigned. And that, I think, is, where's that?
Well, when we talk about signed numbers, we're talking about 2's complement.
No. So he's, let me show you where that is. So that is, where he uses these lowercase s and u. There is a place where he.
Yeah, I mean, yeah, I pasted
Okay,
it in
here you go. Page 6. So yeah, I wish that this were a little more emphasized. But page 6, the second paragraph, maybe I can.
It's what I
No, I
pasted.
don't want to share that because that's
Here,
part
as
of the text.
denotes the signed integer.
Yeah. Does everyone see that?
To the conventions of 2's complement notation, but he doesn't say what those conventions
No,
are.
I see the exercise.
All I was trying to say here is you're not going to be able to prove this mathematically without a mathematical definition of what he means by this question. And unfortunately, that wasn't provided. So we can make something up and go with it. But I'm just pointing out, you can't really prove it given what he's told us in the book. You have to first say, oh, well, let's assume that this bit string alpha, we're going to define that as mapping onto, like, S of alpha is going to be 1 times the rightmost character plus 2 times the second from rightmost character plus 4 times the next from rightmost character and so on. That gives us an actual mathematical expression that we can then plug into the other side and say, yes, if you take that mathematical expression mod 2 to the n, indeed it is itself. But he hasn't actually given us.
Yeah, I feel like he has. I feel like he has, because he says in that second paragraph, he says the formal definition is whatever, and then here s of x denotes the signed integer corresponding to the bit pattern x according to the conventions of 2's complement notation. So he's telling you exactly what it is, and then when you go back to the 2's complement definition, he's told you exactly what that is. So 2's complement, if the high bit is 0, then it's whatever that that bit pattern is. But if the high bit is 1, then you take whatever that bit pattern is and you subtract 2 to the n from that. That is the definition. But I think your point is fair in the sense that it's not in one single place and it's not clearly spelled out. It's I think scattered a little bit, but I do feel like the definitions are there if you kind of at least, you know, sort of piece them together. But that, so let me write it down here, so at least the way I understand it. So S of X, let's not use X, but S of, let's say, alpha. Okay, so alpha is the bit pattern, right? So this is like,
sure
I'll just say
something.
alpha if high bit is 0. Okay, and S of alpha is alpha minus 2 raised to the n if high bit is 1. That's the way I understand it.
Remind me what the high bit is. Is the leftmost?
Leftmost, yeah. Leftmost
Okay.
bit, right. And then unsigned of alpha, which would be just u of alpha, this is always just alpha, like whatever that comes out to be, that's alpha. So alpha is just some string of bits, right? S and U are now interpreting that string of bits a certain way. Does that sound okay?
As usual, I question your notation there. It's not very formal, but yeah, I mean,
Yeah,
U of alpha
I mean,
is
I have trouble,
number,
you know, entering
right?
these
It's not
letters.
actually alpha, but yeah.
But do you feel like this would comprise a definition according to, I mean, like, are you willing to accept this as a definition? And do you feel like it's correct? Like, this is what Knuth has explained, even if you don't feel like he's very explicitly laid that out as a definition?
I have a question about the sign. In the last sentence of the paragraph, when you say that we would describe interaction board informally and formally, it says that we set n to S of X to be the binary representation of n mod 2 to the n, when n is the number of bits in X. So what are you doing? So it's not that. How does that match with the significant leftmost bit trickery that you had in there? I don't get it. So I believe you. I just want to understand it.
Okay, so you're asking about this last sentence. This assignment sets X to the binary representation of n.
Maybe I'm missing the
So this is I feel like this is going in the opposite direction. Like, you've got a number. That's what he's calling capital N.
Mm-hmm.
Right? And we want the signed representation, or the sign, we want to set the signed value of some bits to this number, right? So there's some
Oh, I see.
you know, so you're starting with a number. I think that's where the difference is here. So he's telling you how you can use a number and assign it to the signed representation. Like, what would happen? So he's saying what would happen is this. X, which is sort of the binary representation that you're interested in, at least the signed representation, it would be set to the binary representation of the number big N mod 2 to the n, where n is the number of bits in X. And then he also mentions the possibility of overflow. So if
and then he says C or exercise 5, which is the one we are now.
Which is the exercise 5, right? Right. Right.
So it seems related.
Yeah. So it is related, and I guess it kind of goes back to the content being embedded in the exercises. Like instead of him explaining the stuff in the main portion of the text, he's put some things into the exercises. So Arthur, do you want to explain your comment in the chat?
Not particularly.
Okay,
Just,
so
what it
let's
says.
just read it. The intuition here is that 111 in binary is 7, which is 2 cube minus 1. And then 4 ones in binary is 15. And similarly, and so on, the number 2 to the n is always 1 greater than the maximum possible value of an n-bit binary number. Yeah,
It's
I
one
guess
next to, okay.
the difficult part, or the part that throws people off, or is you have to kind of get over that hump, is that there's the binary representation, and then there's the semantics, like what does this binary representation mean? For unsigned, it means one thing. For signed, it means another thing. So that's what the S and the U functions in some sense are. S of alpha is the signed interpretation, and U of alpha is the unsigned representation. The same binary string, right? Like for example, if I had 0, 1, 1, 1, then the signed representation, let's say S of 0, 1, 1, 1, this is 7, right? If I just have 4 bits, let's say. And then unsigned of 0, 1, 1, 1, well, this is also 7.
It's also 7.
Okay, but let's take 1, 0, 0, 1. Okay, so this one, the signed, let's take the unsigned first. So the unsigned of 1, 0, 0, 1 is 8 plus 1, 9. And signed of 1, 0, 0, 1, what is that?
That would be 9 minus 16.
9, yeah, exactly. So that would be 9, which is, whatever that unsigned representation is. Then you have to subtract 2 to the 4, which is 9 minus 16, right? And that gives you a minus 7.
Yeah. But the reason that we picked 2 to the 4th rather than some other number to subtract at this point is because of the thing I said, right? That it just works out that the way you do 2's complement is you subtract, you take the number of bits you have, which in this case is 4, take 2 to that number. That's how many representations you have possible. And just the signed representations just sort of take the upper half of that range and fold it back on itself. So now instead of representing large positive numbers, they're now representing negative numbers.
Yeah, so whatever that number of bits is, that needs to be fixed. That needs to be understood, and then you can, have these problems. So I think that let's just try to understand what this is saying, and maybe folks can work on it later. But here's what I understand, unless somebody else wants to explain it in the chat. So
I think we're done with this problem. I think we're ready for number 6.
Yeah, let me just explain what the congruence means. So the definition of congruence is you say that two numbers are congruent to each other, modulo something else, if the difference is divisible by that number. So that's all this is saying, that x minus u of alpha is equal to by 2 raised to the n. So that's what modulo means. So whenever you get a chance to work on this, you can work with that definition. It's not really a definition, but it's an equivalency. Okay, we're back. Okay, Arthur has something in the chat for problem 7. Yeah, that's right. So load high tetra, store high tetra, and there's also a reference. Was that in problem 7? I think in problem 8 there's another reference. So Arthur, do you have an answer for exercise 7? Is it true or false? I guess yes or no. Like, could the formal definitions have been slightly different as Knuth writes them? Okay, so for problem 7, Arthur has the actual definition in the chat, and then in the exercise, there's these alternative definitions. Arthur, do you have an answer as well? Yes or no to exercise 7?
I have an answer that's yes and no, but it
Is
disagrees
that
with
for
the
both of
answer.
them, or like one of them is yes and the other one is no?
I think one of them is yes and the other one is no. Trying
Okay.
to figure out why the answer in the book disagrees with that.
Okay. So
I
load high tetra in just sort of informal terms is going to load the high 32 bits of a register with a tetra, right? So we're going to take some value, some 4-byte value, and then instead of normally like we stuff it into the low 4 bytes, we're going to stuff into the higher 4 bytes. And so 2 to the 32 is this 32-bit shift to the left, right? That's a 4-byte shift. So how are these definitions different in the exercise? He's saying that the signed value. Okay, so the original definitions are in terms of unsigned.
Right.
Would it make a difference if it's signed? Doesn't
What?
seem like it should make a difference because you're loading the high 4 bytes, so there's no, sign extension to worry about.
Right.
So I would think the answer is yes for both of them.
The answer is yes for the first one, for the load, because there you're taking a strictly 32-bit quantity. So load, yes, you're taking the 32-bit quantity M4 of A out of memory. turning that immediately into a number, doing things with that number, and putting the number in a register. That all seems to make sense. The store, at least to me, seems not to make sense, because here what we're doing is we have a number in the register. And let's say the number in the register is a 64-bit number. Let's say it has only the sign bit set. So it's like 1 followed by 63 zeros. So that's a very large negative number, and we're going to take that and divide it by 2 to the 32. So that gives us a very small negative number.
Which is the same as right shifting it.
No, we're doing numbers. We're not doing bits anymore. We've done s of x, so now we've got a very large negative number. And I'm dividing it by 2 to the 32. So
Okay.
I now have a small negative number. And now I'm going to floor that. And flooring a negative number still gives me a negative number. Oh, okay. And we store a negative number, but that's okay because the number we wanted to store was 1 with 31 zeros after it. Okay. I at least am willing to buy that, yes. Okay.
Okay, so we agree that the answer is yes. What about number 10? It references this I guess what would you call this? Like a figure or a set of two equations or assignments on page 8. I think this is going to get a little tricky because of the high mult register. I mean, if you want to try it, we can spend a minute on this. You'll have to go kind of back and forth between page 8 and what is being asked for in exercise 8. And essentially it's talking about we've dealt with integers so far, like registers hold these binary representations of integers, but you can think of them as some fractional portion of a number. That's what this exercise is saying. Think of each register as the fractional piece that's to the right of some decimal point, or in general the radix point. And so he starts out saying, assume that there's these two registers and they represent numbers between 0 and 1, and the binary radix point is assumed to be at the left of each register. And then he's saying, go back to page 8, and there's this example over there where the high mult register is set when you come up with a product that does not fit into 64 bits, and then you need this extra 8 bytes for the complete result. And then he says this unsigned multiplication forms a product in which the assumed radix point appears at the left of register RH, because when you multiply two numbers between 0 and 1, the result again is between 0 and 1, and it's going to be even smaller. Like, I don't know if that's really that relevant, but it's again between 0 and 1. And so the high mult register, when it's used for such a product, so now you've got the radix point to the left of the high mult register. So you've got the radix point, and then you've got the high mult register, those bits representing a fraction, and then you've got the destination register, and those bits representing further 8 bytes of that fraction. If the answer or solution or approach is obvious to anyone, let them explain it. Otherwise, I think let's just move on after understanding what this is sort of explaining in the first place. I think the key point here is that he first sets up the interpretation of the registers as fractions between 0 and 1. And so, as I said, You multiply two numbers between 0 and 1, you're going to get a number between 0 and 1. And so, the radix point stays on the left of that, whatever that eventual product is. But now he says, suppose it's a number where the radix point is assumed to its right. So he's broken it up. You're not multiplying two numbers that are between 0 and 1. There's one number that is an integer, as we understand it. But the other register, the Y register, that's a fraction between 0 and 1. So when you multiply two such numbers, what happens to the radix point? So for example, if you had 3 as an integer, and you multiplied it by 0.5, meaning that's the other register, register 5. We know the result is going to be 2. Sorry, not 2, but 1.5, right? 3 multiplied by 0.5 is 1.5. So now you've got a result that has 2 digits, but the radix point is somewhere between those 2 digits. Right. So Arthur is making a good point that my example is in decimal, but Knuth is asking for an answer in binary. But it's easier for us to understand that when you're multiplying a number that's bigger than 1 and you're multiplying it by a number that's smaller than 1 or between 0 and 1, the decimal point or the radix point now shifts. It's no longer always where it was, as in the example when you're multiplying two numbers that are between 0 and 1. So that's the question. Where is that radix point going to be? And again, if somebody has an answer, radix point, Miguel is asking, is the generalization for the for any base, right? Because when we say decimal point, we're really referring to base 10. So radix point is like, oh, base 2, base 3, base 4, whatever. I think I know what the answer is going to be, but I haven't really thought it through. But essentially, we have to now figure out how many decimal points, like how many leading zeros are in that fraction. Like if I were talking about decimal multiplication, so 0.5 would mean the decimal point will shift 1. And then if it were 0.05, the decimal point would shift 2 places. And that's sort of my take on it.
So the way that I would tackle this one, problem number 8, is when you multiply two numbers. Now, when you did your example, you picked numbers like 0.5 or something like that. It's easier to get an intuition for it if you think about ranges of numbers. If I have a number between 0 and 100, and I multiply that by another number between 0 and 100, my answer is going to be between 0 and 10,000. If I have a number between 0 and 100, and I multiply it by a number between 0 and 1, a fractional number, anywhere between 0 and 1, my answer is still going to remain between 0 and 100. But I'm going to have more digits. I'm still going to get that same 128-bit result in MMIX. But it now represents something that's only in the range 0 to 200, or 0 to 2 to the 64th. And so that means, well, you must have 64 bits of the answer and then 64 bits of stuff after the decimal point, which is what you have in this case. If you start with two numbers between 0 and 1 and you multiply them together, you end up with a number between 0 and 1. So all 128 bits of the result are to the right of the decimal point.
Yeah, I think that's good. But the question again is, where exactly is that radix point?
64 bits.
Be?
It's right in the middle. You have 128 bits, and the answer number 8 is it's right in the middle. 64 bits from the front, 64 bits from the back. Because the number that you get out is going to be in the range 0 to 2 to the 64th. Right? You put in two numbers to multiply. One of them was in the range 0 to 2 to the 64th. The other one was in the range 0 to 1. When you multiply these numbers, the answer is in the range 0 to 2 to the 64th. So you need 64 bits to represent the answer, the part of the answer, and then you have 64 bits after the decimal point.
So then the radix point is between the two registers.
Yes.
So it's to the right of the high mult register,
yes.
and it's to the left of the destination register.
Yes.
Okay, let's move on. Let's look at number 9. Does the equation signed? Okay, so let's go back to div, because it's referring to the div instruction. So the destination register is X, and we're dividing register Y by register Z. Right, and the destination register holds the quotient. So when you divide Y by Z and X is the quotient, then does the equation that's given, which is the signed value of the dividend or Y, is that equal to the quotient, signed quotient times the signed divisor plus the signed remainder? So not like normal division and its inverse multiplication. So you would expect that. And so now the question is, does it always hold? Like, are there some cases where it may not hold, may not be true? And this is for signed.
I think it holds, right? Even if set is 0, Y will be indeed the remainder. So for the rest, it's just a regular thing.
It certainly holds for all normal cases by definition, because R it just gets set to the remainder, and it also holds for division by 0, because in that case,
we just set Y to the register, the remainder.
Yeah, so we have to go back to what happens when you divide by 0. I think the destination register gets a 0.
No, you put Y in the remainder.
You put Y into the remainder, and the destination register X gets 0, and so it still holds in that case.
Okay. Yeah. So the destination gets 0, and remainder just gets Y. So when we plug in those values.
So question 10 then is asking for the only case that we haven't covered yet. And that's the example of div in which overflow occurs. When does overflow occur here? And in that case, does that equation hold or not?
So I guess those are like two separate questions, because the first question is just give an example. I mean, number 10 is strictly speaking, just saying, do you have an example in which overflow occurs?
I believe there is only one.
You believe what?
I believe there is only one example you could.
Okay, so what is that example?
Well, that's the question. I mean, I can give you right away. I thought maybe Miguel wanted to think about it a bit more deeply.
So in the division, we always take the ceiling, the floor, the division between Y and Z.
Right.
So I can only imagine that what is in the register, when you apply the sign operation, that overflows. I cannot see the division itself overflowing.
When you
taking the S of X is never going to overflow by definition.
Yeah, so
you're looking for a case where
you always go to the floor. So
you're looking for a case where when you divide whatever by whatever, the answer is bigger than what you put in.
Yeah.
At least it doesn't get smaller. For most numbers, when you divide an integer by another integer, the answer gets smaller.
So only like Y be very, very big and Z be very, very small.
Yep.
So anything that, no, the other way around, sorry. But
Well,
no,
y.
cannot see it.
Yeah, y being big and, wait, I don't remember which one is which either. But anyway, yes.
Well, we're dividing y by z.
Bottom needs to be small.
Yeah, you're dividing y by c. So c has to be very, very big and y very, very small.
Other way around. The divisor wants to be very small, but not 0. And not 1, because that would be trivial. Dividing anything by 1 just gives you the thing again. But what is another very small number that we know of?
Okay, so
1.
if we think of 2's complement and sort of the negative range
Because you
of
multiply.
numbers, right? We know that the signed numbers can go between -2 to the n minus 1. Sorry, -2 to the n, and sorry, -2 to the n minus 1, and strictly less than 2 to the n minus 1, right? If you have n bits.
Mm-hmm.
So it's interesting that there's an asymmetry here. On the negative side, you can actually go 1 lower than on the positive side. Because on the negative side, you can actually equal -2 to the n minus 1. But you can't do that on the positive side. On the positive side, the signed representation has to be strictly less than 2 to the n minus 1. So what this is suggesting is that if you take that smallest negative number and you divide it by something to make it positive, that is not going to be possible. So what is that something? By -1, yeah. So if you divide something by -1, that's going to flip the sign. But since the negative range has this asymmetry, there's one negative number that you can represent that's at the end of the range that you cannot represent as the positive number. So, you divide it by -1, you can't flip that sign. It's not possible.
And
Yeah.
indeed, in that case, the equation does not hold.
The equation does not hold.
I cheated and looked at the answer.
Let's see what the values are in that case. So the destination, oh yeah, because now you have overflow. What do you get there in overflow? You get 0? Do you get 0 in the destination register in X?
Yes.
So 0 plus the remainder. And what is the remainder? What do you get for the remainder when there is that overflow?
The remainder is just the answer mod, it's the remainder. And in this case, there is none because one divides evenly into the other. So
Yeah. Okay. Good. Number 11.
Although I'll point out there's one more thing in the answer that Knuth is sneakier than us also.
Okay.
The equation also does not hold in the case that X and Y are the same register. We didn't do that at all, but yes. Right, if you're overwriting one of the operands, this is actually on a machine and it overwrites operands with the answer. And so you might not have the S of $y might no longer have the value it had at the start of the instruction.
Yeah. I should add that to my set of examples where I'm reusing the same register as the destination and see what happens in different cases. Yeah. Okay. Number 11, true or false. Both the signed and the unsigned multiplication produce the same result in the destination, no matter what numbers you're multiplying. Signed and unsigned.
I'm fairly confident that that's true.
Well, the main difference is that unsigned is never going to overflow.
Right, but he's not
So-
asking about the overflow flag, he's just asking about X.
But what happens with overflow does occur for the sign multiplication in terms of what's in the destination register. Could that be different?
I don't think so, because remember, overflow is different from something like divide by zero. Where divide by zero, there is no answer, and so we had to make up something sort of ad hoc to put in the register. With all the rest of these operations, there is always an actual mathematical answer that we're trying to represent, and overflow is just saying, well, we don't have enough bits to represent it, but it's still the answer. I am also fairly confident that for division, this is not true. And again, I would look at a number where you're dividing by something that's either divide by -1 or divide by like huge negative number, or sorry, huge positive number, right? Those had better be different.
So look, to understand you say that multiplication is the same, independently of the overflow. Is it because it makes no sense to multiply a minus any? If you are comparing unsigned with sign, you are assuming that the inputs are always positive, because otherwise you couldn't use it in unsigned. Or are you saying that a negative number translated to unsigned?
Well, the
Makes sense?
interesting cases would be when,
So
I guess, when one or both of the numbers are negative,
that's the
right?
question I'm
Because
asking.
then multiply unsigned would be like some big positive numbers.
Right, that's
right?
what you would do, right? You will translate the negative number to unsigned and then multiply that with the other number. So what happens there?
So Arthur says signed of x times signed of y is unsigned of x, maybe -2 to the 64
Right? I think this
times the
can do
unsigned
that.
of y, maybe -2 to the 64. I guess, yeah, we should look at sort of the definitions that he has, right? There's these definitions mod 264, and this should always be congruent to unsigned of x and y, unsigned x times x, unsigned y, mod 2 to the 64. Okay, so what is the answer to A? Arthur, you say it's yes for A and no for B, or false for B?
Right.
And what is the case when it's false, or what are the cases?
For division, we should look at a case where the divisor is like all bits 1. So for signed division, we're dividing by -1, and for unsigned division, and so that will keep the magnitude of the answer the same as the input. But for unsigned division, we'd be dividing by a super large number.
It'll be 2 to the n minus 1.
Make the answer 0. In one case, we have, again, I forget, we're doing like y divided by...
Would it be just one case then, or would it be just any?
No, it'd be a whole bunch of cases. But this is like the easiest one to see.
Okay, so dollar, if we look at it as signed, we're dividing by -1, and so we're just essentially flipping the sign of $y. But then if we divide, okay, thanks, Miguel. If we divide by, if we use it as an unsigned, then that's like a really huge number. And for one thing, we would probably be setting the remainder.
So the answer is going to be 0. Yeah. Oh, the answer in the y divided by max int, that's 0, unless y is also max int, in which case 1.
Yeah.
You can't get any other answers there.
Yeah. Okay. Number 12 looks interesting. Let's try that. So add unsigned never signals overflow. But we might want to know if a carry occurs at the left when adding y to z. Show that the carry can be computed with 2 further instructions. So we're adding 2 really big numbers. The result does not fit into 64 bits because there's some carry, there's some 1 at the very end, but there's no bit for it to be stored in. How could we figure out the carry, whether there was a carry of 1 or the carry was 0? So you're saying there is a carry if and only if the sum is smaller than either one of the inputs.
And the operation is commutative, so it doesn't matter which of the inputs you pick.
If the sum is smaller. So then you're saying we should compare $x with either one. So you're saying just pick one of them. So compare signed, right? Or compare unsigned.
We're doing everything unsigned here.
Okay, so we do a compare unsigned of $x and let's say $y. And then what? Then we need to. So we need one of those compare if negative instructions.
Yeah, this could be particularly tricky if we remember the trick from number 9, which was what happens if they're the same register. But just to compare x with y, we would use the CMPU instruction, right? Is that an instruction?
CMPU is an instruction, but that one, yeah, I guess you could use that because that will result in either a -1 or a 0 or a 1. It tells you from the value what the comparison ended up being. Like if y, so let's see. Compare unsigned, page 9, bottom of page 9.
Yeah.
It will set the destination to be -1 or 0 or 1 if the first operand is less than or equal to or greater than the second. The second operand is less than, equal to, or greater than the third operand. So So isn't that just one extra instruction? Then why?
Well, it depends what he means by the carry. Like, does he mean to get the answer back into the overflow flag?
No, I think what he's saying is he wants the value of the carry.
Yeah.
So he wants a 0 or a 1 in some register at the end. He wants that answer.
So now we've got a -1, 0, or 1, and we need one more instruction to turn that into just a 0 or a 1.
Yeah.
And then as long as X and Y are not the same register, we don't really have a problem. We don't have a general formula, but we just pick whichever one still has its old value and compare with that one. And if X and Y and Z are all the same, then we shouldn't have been using add in the first place. But he has a trick for that in the answers too.
Oh, okay. All right. I think we have a pretty fair idea here. We just need to figure out the exact register order and the exact second instruction. Similarly, number 13. Suppose, well, not similarly, this is a bit different. Suppose there was no signed add, we only had unsigned add. How could a programmer tell whether overflow occurred when computing the signed sum of two numbers? Well, this is just going to be a wraparound thing, right? You add two numbers, and if overflow occurs, the destination will end up being negative. Well, all we're saying is we don't have a signed add, but we have everything else, right? So we do have signed operations. We just don't have signed add. We only have unsigned add. Adding two numbers and then the sum is, add two signed numbers and then the sum is.
Right, so we have an add instruction that gives us the right value in the register itself, but it doesn't signal either carry or overflow. And we're not asking to just detect the carry, which is what 12 was asking for. We're asking specifically for whether this would have been overflow, supposing that these two numbers were signed to begin with. So for example, if they were like 4-bit numbers and we're adding -8 and -8, and that comes out to -16, that's an overflow.
No, but wait a second.
Okay.
If you're did you say 8 or -8?
I said -8, and I said I'm working
so
with
-8 meaning, because we only have add unsigned. So
well, what we have here is we have the add unsigned instruction, and we're using it on these registers.
Right, and then
these registers represent signed numbers. We're trying to compute the signed addition. We haven't got a signed add. We've only got unsigned add. How do we use unsigned add to simulate signed add?
Yeah.
And so this is similar to number 12, but not the same, because overflow is not the same thing as carry.
Right. So -8 will be 1 000.
Mm-hmm.
Right? And so let's just take Z to be the same. So 1 000 plus 1 000. This should overflow.
Right.
And what's going to be in the destination with add unsigned?
All zeros, because the answer, as far as ADDU is concerned, this is 8 plus 8, which is 16.
Which is 16.
We have 4 zeros and we get 1.
Right.
Carry.
So now we need another instruction, or maybe more than one instruction to figure out.
Yeah, so the trick here, similar to the previous trick. The previous trick I knew off the top of my head. This one, Knuth tells you in the answers again. But signed addition overflows if and only if your two things that you're adding, your two add sign, and then when you add them together, you get something of the opposite sign. If that happens, you have overflow, and if that doesn't happen, you're okay. They have opposite signs, they will never overflow. If they have the same sign and the answer has the same sign, you're okay.
So we just need to check the sign. So I guess we would need, can we do this with one instruction? I think we would need at least 2 instructions.
His answer has 5 instructions, and I am inclined to get nerd sniped here trying to figure out why they're all needed.
Okay, so maybe I'll spend some time on it, or if somebody else wants to understand that the 5 so yeah, 5 instructions sounds like quite a lot, but
one of them is the add, but he's got 4.
Oh, then 4 after that. Okay, so then it's 4. All right, cool. So we can try one more. Arthur, do you want to pick one, or somebody else wants to pick one? How about number 17?
Oh, geez.
Let's look at 17 or 18. Well, 18 is M23. We don't need to prove this, but maybe we can just understand like why this would work.
By the way, I think number 20 is a good one to end on.
Okay,
maybe.
let's look at number 20. Oh, okay. Number 20. Show that 2 cleverly chosen MX instructions will multiply by 25 faster than the single instruction if we assume that overflow will not occur. So I guess here he's probably referring to the timing section that we haven't really covered, right? Because otherwise, how would we know that 2 instructions could be faster than a single instruction?
True. The intuition here is multiplication is slow.
Yeah, okay, so let's take that as sort of the benchmark, that multiplication, a single multiplication has some cost associated with it, and it's relatively higher than add, subtract, compare, and we'll leave div
except
out of
division, I think.
Hmm?
As long as you don't use division as one of your 2 instructions.
Yeah. Okay. So yeah. So can we replace the single multiplication by add, compare, subtract? If we're just multiplying by 25, so Arthur, you're saying 25 is 16 plus 8 plus 1.
If it only had 2 bits set, then I would think, oh, okay, we're just looking for a way to sort of shift it over and then shift it over again and then add them together, which is still 3. But now we've got 16 plus 8 plus 1.
What about those special 2 ADDU, 4 ADDU, 8 ADDU, 16 ADDU?
Ah, yes.
Right?
That sounds good. And also the 8 plus 1 looks to me, with my x86 background knowledge, like an effective address. And I seem to recall there was a load effective address instruction in MX as well, although he probably calls it something different.
I'm not sure what you mean by effective address, but there is a load address, but that's just a simple add.
But one of them is
what do you mean by effective address? You mean calculate the base and the offset, or?
Yeah, where the base is multiplied by some small number.
But that's I think basically these 2 ADDU, 4 ADDU, if I understand you correctly. But
yeah, okay. Well, certainly the ones you're talking about are going to help here a lot, and are probably.
But how do we get 2? Because 16 plus 8 plus 1, that.
Well, we use one of these for the 16 plus 8. Ah, yes, right. So what do we want to do here? We want to have 2 ADDU as the first instruction. So let's say 2 ADDU of into some temporary of x and y. What are we doing? Yeah, or y, just y. That's right. Y and y.
Okay, so couldn't we do it like 16 ADDU and then 8 ADDU and then the add piece? So in the 16 ADDU, we're incrementing by 0, and then the 8 ADDU increment by 1. Right? Because each one of these will multiply by that constant and add an unsigned value as well in the same instruction.
I didn't quite follow what you said, but it's probably the same thing I just pasted. Does that work?
2 ADDU gives you 16, and then you want to add the same value once. Okay. Yeah. This looks right. Because the first time we are just simply multiplying it by 2. No, wait a second. You've got $y and $y in the, that would be like y squared. No, what, sorry, that's y, you're multiplying y by 2, and then you're adding y to the, okay, you have that in the comments actually. So 2y plus y, so that's 16y plus 8y, 24y plus 1y, 24. Yeah, that works out. That works out. 8 times, wait a minute, 8 ADDU is 8 times C. Yeah, okay. You actually multiply the third operand by the constant, not the second operand.
So in that second instruction, they should be flipped around. Yeah.
No, wait a second. I think I have it wrong. You do multiply the second operand by the, so I think the second instruction is wrong. The order should be flipped. But otherwise it looks good. Thank you, Deepa. Okay, so good. So at least we have some idea of what to expect from these exercises. Now these are, from the Fascicle, and so all of these exercises are kind of new compared to, stuff that he had in his original volumes that have been carried forward. So it's kind of interesting to see, or it'll be interesting to see these compared to some of the older ones. But yeah, so next time around, we will be let's see. Yeah, so this is where we had kind of left off last week, and hopefully we can finish up all the instruction set, or at least the main portion of the instruction set that I feel will be not good enough for us to start on the algorithms. But then there's a couple of full-fledged programs that we will look into for more of the assembly language. So there'll be a bit of that in next session, and then the following session we'll look at 2 or 3 other programs, and that should pretty much do it for MMIX. I think we're good to go there. And then I have the meetup schedule, sort of the tentative schedule on the repo. You can have a look at it if there's any feedback you want to give. But there's a couple of sessions that we have for discussing that. So, all right. Thank you very much for attending. See you folks next time.
Next time.
Bye.